Suggestions? It might have to be the case. Let's try that. Oh, it's running lots of PowerPoints. Yeah, but is this going to do anything different? Oh, fabulous. Okay. Thanks. That was a good suggestion, Juan. Okay. Extra 16. Extra bonus points for that one. All right. Today, we are going to talk about material functions. And as I indicated last time, I'm almost done with the exam, so I'll have them on Friday for sure. Some people are going to be fine, and some people are going to be a little bit less happy than they think. So, the last problem, the big one, didn't go badly, but it was the others that death by 1,000 cuts, something like that. It's not that bad. It's not death or anything. We could have done a little better on those. Anyway, we'll talk about that on Friday. So today we're talking about material functions, and I've described these as kind of ASTM tests. What they are different standardized tests that we're going to use in two ways. We're going to use them to describe material behavior, so it's a shorthand for how the material behaves. And we're already doing that when we say it has a high viscosity or it has a low viscosity. We're already using a material function, the viscosity, and we're using it to describe how a material behaves. And because we know what that means, high viscosity means that it generates a lot of stress during flows, or when you'd say pour it and subject it to a constant stress, it pours more or less quickly. So all of those are actually related to the issue of creates a lot of stress during a shear flow. So there's more material functions than viscosity, and we're just going to go through them. But we're also going to use them to test constitutive equations. So the one constitutive equation we have is the Navier-Stokes. The Newtonian. So this is our only constitutive equation, and we know it doesn't work for most polymers. So what we're going to be doing is using this constitutive equation and we'll use this to predict material functions. So for instance, we can predict viscosity in the sense that we can put in the flow that goes with viscosity, and we'll see what the stress is predicted to be, and then put that into the definition of material function, and we'll get out the prediction for the viscosity. And then we're going to make new constitutive equation and do the same thing. We're going to use it to predict material functions, and we're going to then see if it matches what we know the outside world does. So what I'm going to do in the next two chapters is I'm going to define material functions and show you how to use them. And then the experimental behavior chapter is all these ways materials actually behave using the vocabulary of the material functions. So this will be, say, describe real fluids. So that's what I've got summarized on this slide. that we have these material functions, and one of them is the viscosity. And so here's a new symbol for viscosity, eta. And it's not just the world deciding that mu wasn't good enough and we're going to switch to eta or some sort of a culture difference. There's actually a subtle meaning difference between viscosity. This is the non-Newtonian viscosity. This is the general viscosity, whereas what we've been talking about is the strictly Newtonian viscosity. But there will be other material functions that are based on stresses and based on particular flows. And these are some of them, G prime, G double prime, and the relaxation modulus, G of t. So we're going to be doing this part. We're going to be predicting material functions and comparing them to measured and using them to decide what constitutive equations are best for our material. All right, so now a material function is, the definition of material function comes in two parts. And the two parts are the kinematics and then the actual definitions themselves. So the kinematics, kine, comes from the Greek for motion. Okay, so these are the motions that you have to subject the material to in order to be talking about a particular material function. And this is going to be either shear or elongational flow. So we choose the flow, shear or elongation, and then we choose the details of these time functions that appear inside the definition. And once we've made those two choices, we've completely chosen what to do to the material. We've chosen the kinematics. Then we'll either have a material and measure it in the lab, and if it's shear flow, we'll measure these three stress quantities. If it's elongational flow, we'll measure these two stress quantities. Or we'll take a constitutive equation and predict stress quantities, one way or the other, and then we'll compare the two, predictions to experiment. So let's start with something specific, because talking about this too generally just leads to confusion. All of my slides that define material functions look like this. They have the kinematics at the top and the material function definitions on the bottom. So everything that's on the left-hand side of a triple equal sign is a material function. Everything on the left-hand side of this triple equal, which is the define equals, is a material function. And so this is the definition of viscosity. This is the definition of the first normal stress coefficient. This is the definition of the second normal stress coefficient. So what does this slide say? This slide says that the material functions, viscosity, first and second normal stress coefficient, are defined for this flow, either imposed or put into a constitutive equation. And then, because we know for this flow, there are only three stress quantities, tau 2,1, first normal stress difference, second normal stress difference. So you can either measure these or predict these from a constitutive equation. Then once you have them, you divide them by this quantity, which is a quantity that appears in the kinematics, and then you get your prediction. Sounds complicated. Let's just do one. So I'm going to predict it for the only constitutive equation we have, which is shear flow. So here's the definition slide, and I'll work over here to predict what the viscosity is and what the first normal stress difference is for Newtonian fluid. Okay, so that's my first example. Predict viscosity, first normal stress coefficient, second normal stress coefficient for a Newtonian fluid. You will see problems on the exam, problems on the homework that look like that. Predict, name the material function from, name the constitutive equation. The constitutive equation is the Newtonian fluid. The material functions are, in this case, viscosity, first normal stress, and second normal stress. So just by using these terms, I am saying that the flow field must be the one on this slide. It must be shear flow with the function being a constant, which we call gamma dot naught. So that means that the velocity imposed is going to be gamma dot naught x2, 0, 0. So this is totally different from the idea of solving for the velocity field. When we solved for the velocity field, we said, take a Newtonian fluid and put it in this situation. Put it between two infinite plates and move one of the plates. Put it between two infinite plates and blow on it with a pressure difference. Put it on two sloping, upwardly sloping plates. Run it down a wall. Put it between a cup and a bob and turn the inner cup. Those were all flow situations, and we said solve for the whole velocity field. Right? That's one use of constitutive equations, and the momentum balance. Here we're saying this is the velocity field. Predict things that are related to the stresses. So to get these things, we need to know what their definitions are, and they are defined again on this slide. So viscosity, first normal stress, and second. And to use those definitions, we need those stress quantities. We need tau 21. Gamma dot naught is a quantity that may possibly appear in our answer. It's a quantity that is part of the flow that we're talking about. Psi 1 is minus tau 11 minus tau 22 over gamma dot naught squared. Why is it gamma dot naught squared? It's arbitrary. I'll give you an argument why at some point, but for us at this point, it's just a definition. That's just the way it is. Psi 2 is minus tau 22 minus tau 33 over gamma dot naught squared. So what do we need? We need these. We need to predict the stresses for a Newtonian fluid. And we can do that because we know that tau equals minus mu gamma dot, del V plus del V transpose. All you need is V, and we've got V. Okay? Very simple. So let's do it. For Newtonian fluid, the stress under all circumstances is minus mu, which is a parameter of the model. It's just part of the model, del V plus del V transpose. Yes?
Why is it that the nomenclature, I mean, why do you write your, what is it, the fork?
Mu.
Mu. Why do you write it that way? Just take out the minus sign and just write a T22 minus, I mean, tau 22 minus tau 11 is there. Is there a specific reason why that minus sign is there? I mean, in your slide. I don't know.
This minus sign?
No, in the fork.
Oh, here. Why don't I switch them?
Yeah. Why don't you just put?
Well, there's a. As I said when I first introduced stress, there are two sign conventions for stress. One is the one we use in chemical, and one's the one we use in mechanical. When you use the mechanical one, this minus that's out in the front doesn't appear. So it would be kind of confusing to be switching these back and forth all the time. So we try to leave that minus sign, the chemical engineering minus sign, we try to leave it out front so that if you're a mechanical engineer, you're less confused. Once we're in this nomenclature, then we don't have to worry about signs anymore. It's only when a tau appears that that sign convention difference makes a difference. So you may see, in the literature, you may see this without the minus sign, and that just means they're using the other stress convention. And you'll certainly see this without the minus sign. Good question. All right, so this is the Newtonian fluid. Now, of course, you know this is the viscosity, but think of this as a parameter of the model. It's just a parameter. Okay, think of it as a material parameter of the model. So we need del V and del V transpose. So here we're back to del V. Del V is d by dx EP, Vm EM. The V goes in there. dVm dxp EMEP. And this is a tensor, dV dx everywhere. And this is the columns and the rows. So these are V1, this is V2, this is V3, and the rows are X1, X2, and X3. But we know the velocity field. It's defined as part of the material function. We know that V is equal to gamma dot naught x2, 0, 0. So what's dV1 dx1? 0. There's no x1 here, right? What's dV2 dx1?
0.
0, because V2 is 0, right? So V2, 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 these are all 0. V3, 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 these are all 0. dV1 dx1 is 0. dV1 dx2, gamma dot naught. That's a constant. This is still our variable x2. dV1 dx3, there are no x3s there, 0. So that's del V. Del V transpose is rows and columns reversed. And so gamma dot is 0, gamma dot naught 0, gamma dot naught 0, 0, 0, 0, 0. So we've calculated the stress for a Newtonian fluid in this flow. The stress tensor is minus mu gamma dot, del V plus del V transpose. So that must be 0 minus mu gamma dot naught 0, minus mu gamma dot naught 0, and then all zeros. So for this flow, for the flow with this velocity, this is the stress at every point in the fluid. It's independent of time. There was no time in it because back here when we specified the velocity, we put a constant in where the time function appeared. This is the simplest flow, which is steady shear flow. So this is the stress at all times and all places. It's a constant. There's nothing in here that varies. Now we go and we get the definitions of our material functions. And we use the definitions. Viscosity is defined as minus tau21 over gamma dot naught. Gamma dot naught is a parameter of the steady shear flow. So it's minus tau21 over gamma dot naught. So the material function called viscosity is given by this parameter of the model. And that's why we call it the viscosity as well. But the fundamental definition of viscosity is this. It's the shear stress when this particular flow is imposed divided by the shear rate when this particular flow is imposed. We can also calculate psi1 and psi2. Psi1 is minus tau11 minus tau22 over gamma dot naught squared. Tau11, tau22, this is 0. psi 2 minus tau 2, 2 minus tau 3, 3 over gamma dot naught squared. Tau 2, 2, tau 3, 3, 0. So the Newtonian constitutive equation says that if you put a sample between any shear flow, it will not produce normal stress differences. It will not. It's not in the constitutive equation. Okay? So this constitutive equation is incapable of producing, say, rod climbing. Incapable. Because we saw that rod climbing required a first normal stress difference effect. So we had a constitutive equation. We took it and we put the definitions of the material function into it, and we got a prediction. What do we actually see? Do we actually see that the viscosity is a constant and that the first and second normal stress differences are 0? And the answer is no, we do not. Okay, for polybutadiene, this is some data that's reproduced from the book. There is a shear thinning viscosity, and there is a non-zero first normal stress difference that varies with shear rate. Actually, I didn't discuss yet this. This parameter, there's a subtlety to this parameter, the shear rate. This is not gamma dot naught, and that's not a typo on my part. Let me talk a little bit about that. Just before I do, let me point out why the first normal stress difference was tau 1, 1 minus tau 2, 2 divided by gamma dot naught squared. Okay? By dividing by gamma dot naught squared, we got this function to look like it does, which is that it goes to a constant value of the plateau and looks kind of like a shear thinning viscosity value. If we hadn't divided by gamma dot naught squared, this would be variable up here, right? Because it's coming to a constant. In fact, if I show the next slide, here's some more data. These are more polybutadiene solutions. They're also shear thinning. And they also have non-zero first normal stress differences, all of which come up kind of to a plateau when you define the material function the way we did. So that's the reason. It's a very practical reason. It just looks good. And why does it look good? Because there are many materials for which N1, meaning tau 1, 1 minus tau 2, 2, approaches, doesn't approach a constant, but approaches like, it goes like gamma dot squared at low rates. And so if you divide that out, it approaches a constant. Let me discuss this gamma dot. This gamma dot is the magnitude of the tensor gamma dot. So here we calculated the tensor gamma dot, which for this flow is this tensor. And we know that we have, as defined, a tensor magnitude. We studied a little bit about that. The magnitude of a tensor is defined as A dot A square root, A double dot A square root over 2. This is a positive quantity, and this is why we use the magnitude of a tensor, because this shear rate can be positive or negative in shear flow, and we want a positive quantity. So let's calculate this number for this tensor. Gamma dot double dot gamma dot is gamma dot ij ei ej double dotted with gamma dot pk ep ek. So the double dotting means we dot the nearest 2, so that's delta pk. We dot the farthest 2, that's delta delta pj, delta jp, let's say, and the farthest 2, ik. And delta, I becomes k, gamma dot I, j becomes p. This one stays the same. And this says double sum p equals 1 to 3 k equals 1 to 3 of gamma dot kp gamma dot pk. So it's 1, 1 times 1, 1. 1, 2 times 2, 1. 1, 3 times 3, 1. 9 times. One, 1, 1, 2, 2, 1, 1, 3, 3, 1, 2, 1, 1, 2, 2, 2, 2, 2, 2, 3, 3, 2, 3, 1, 1, 3, 3, 2, 2, 3, 3, 3, 3, 3. So there were only 2 terms that were non-zero, right? There was 1, 2 times 2, 1, and 2, 1 times 1, 2. Okay? So that means this double sum is equal to 2 gamma dot naught squared. That's gamma dot double dot gamma dot. If I divide it by 2 and take the square root, I get the absolute value of gamma dot naught. So that quantity, when we write it just as this, gamma dot, this is the magnitude of the tensor gamma dot. And in the case of steady shear flow, that's equal to the absolute value of the shear rate. So we've looked at a few examples of how material behave, and what we see very clearly is that the Newtonian predictions are not valid. There are many materials for which it is valid. Newtonian predictions are valid for water, oil, and air, but they're not valid for polybutadiene solutions. They're not valid for these polybutadiene solutions at a variety of molecular weights. They're not valid for this polydimethylsiloxane, which has a constant viscosity for a while, but then it has a shear thinning viscosity. Constant viscosity for a while, then shear thinning. These are linear branched materials, polydimethylsiloxane. So our conclusion is that the Newtonian constitution is a loser for polymers. It always predicts a constant shear viscosity, and it does not predict the shear normal stresses that we definitely see. So we need to take this constitutive equation and change it. And that's what we're up to in this class. And because we saw that when we put this equation into shear flow, whatever was out front turned into the viscosity prediction, we could try to fix it by putting something out front that varies with shear rate. So if we invent this constitutive equation, we can ask the same question: what does it predict in shear flow? And the calculation method follows the same. So what does this constitutive equation, tau equals minus m gamma dot naught times del V plus del V transpose, predict for steady shearing flow? As soon as we say steady shearing, we know we're talking about V equals gamma dot naught x2, 0, 0. That's steady shearing by definition. And so we can go through all the same steps, but del V plus del V transpose is going to be the same because V is the same. So that means gamma dot, the tensor, must be 0, gamma dot naught 0, gamma dot naught 0, 0, 0. No matter what the constitutive equation, because the velocity field's always the same, this gamma dot must always be the same. Once we have this, though, we can plug it into a constitutive equation and get the predictions. So this is going faster already. If tau is minus this function m, some function of shear rate, times this tensor, we can calculate the viscosity that's predicted. The viscosity is minus the 2, 1 component of this tensor divided by gamma dot naught. What's the 2, 1 component of this tensor? Yeah, m, which is a function of gamma dot, times gamma dot. And there's a minus sign and a minus sign, which cancel. So these guys can cancel, and we get m. So whatever function we put out front, that's the function that we predict. So we can get smart and just put out front what we know the material does. Okay? We can just invent a function, m, and make it slope downward at high shear rates and come to a constant value at low shear rates. Just put the answer right in. Very appealing. We know it's going to come out right. Okay? This is a function that slopes downward on a log-log graph. It's a power law function. This says below some critical shear rate, which is when it turns over, below some critical shear rate, it's going to be a constant, which I'll call m naught. And above a critical shear rate, it's going to be this function. All right? So problem solved. The only problem is, what does this model predict for psi 1? Right. It predicts 0 because those are still 0. And for psi 2, which we haven't even talked about, it also predicts 0. So we fixed it the easy way for viscosity, but it is not going to be easy to fix it for first normal stress difference. So that's the summary here. This is our constitutive equation. This is del V. This is del V transpose, del V plus del V transpose. No matter how you slice it, it's not predicting normal stresses. And now we can be very mathematically about this. Any constitutive equation that just has junk out front, no matter how complicated and interesting this junk is, no matter what we put, when we multiply it by del V plus del V transpose for steady shearing flow, this is going to be del V plus del V transpose for steady shearing flow, always. And these will always be 0. And there's no subtlety to 0 minus 0. It's 0. So we will never, never predict normal stresses with a model that just does that. Okay? So we have to make up something else. We could add something that lands along the diagonal. So if we're just making up stuff in the front, why can't we just make up new stuff for the diagonal? Why not? Okay? We could try making up different things with Einstein notation. We can, instead of del V plus del V transpose, we can go del V times del V transpose and put wacky functions out front. We can go nuts. We can do both. Del V transpose, and del V dot. You know, we can just go completely nuts. They did. This is what people tried, looking at these things and seeing if they could get something that would predict something along the diagonal with the velocity vector that goes along with steady shearing flow. There's a lot of missing underlines here, but this is the velocity vector V. Okay, problem is that there's more things to try, you know, than we have the energy to test. And we don't have to be that arbitrary. We can be a little smarter about it because we can observe different materials and see what they do and see if we can deduce what the form of the constitutive equation has to be. Okay? So let's try another material function to get more observations under our belt. So as I said, every time I give you a material function, it'll come on a sheet like this. There'll be kinematics at the top. There'll be material functions on the bottom. I don't expect you to memorize these. They're pretty straightforward, and I've got a lot of them memorized. So there's been times on tests when I've forgotten to tell you one of these. But it's not because I expected you to memorize it. It's because I forgot. Okay, so keep that in mind. If you ever need one, I'll tell you what it is. This is not the kind of thing one has to memorize. All right, here's another material function. It's called startup of steady shearing. Maybe you can guess how it goes just from the name. All right, Here's our general shear flow with sigma dot, which is a function of time. And now sigma dot's no longer a constant. It's two constants. It's 0 below the time that the clock starts, and it's now shear flow once the flow starts. So this is a step function at time t equals 0, and it goes from not moving to moving. We will measure the shear stress and the first normal stress and the second normal stress as a function of time. And we will define material functions that go with this set of kinematics. And they will be called eta plus, which is a function of time, psi 1 plus, and psi 2 plus. Okay. So we've got an interesting material function. Do you know what it's predicted to look like for Newtonian fluids? You can maybe guess. Or we could just calculate it. Okay? So any material function we can calculate if we have a constitutive equation and sufficient mathematical skills. There will eventually be constitutive equations that are complicated enough that you need advanced mathematical skills to do such a prediction. The Newtonian fluid is not one of them. It's very simple. So let's do it. And I want you to be watching the routine because I'm going to be asking you to do this. What's the routine when I say, predict a material function for a given constitutive equation? Well, here's the question. What are eta plus, psi 1 plus, psi 2 plus for a Newtonian fluid? All right? Just like in all engineering problem solving, at least in academia, there's a lot of code there. Okay? For a Newtonian fluid is code for use the Newtonian constitutive equation. Eta plus, psi 1 plus, psi 2 plus is code for use the kinematics that go with this. And there's a very prescribed set of kinematics that go with that, and they're on the slide. The kinematics are that the velocity vector is given by sigma dot of t times x2, 0, 0. Shear flow, unsteady, where the sigma dot function for this flow is given by 0 until the flow starts, and a constant value called gamma dot naught after the flow starts. To evaluate the constitutive equation, we need gamma dot. Gamma dot is del V plus del V transpose, so we need del V. So del V again, and we can do Einstein notation again. Or we could grab our old slide and copy it down. It's dV dx, dV dx, dV dx, dV dx, dV dx, etc., 9 times. The derivatives go across the rows. The velocities go down the columns. Turns out the same as it did before. A little bit different because this is not a constant out front. But, you know, V2 is still 0. V3 is still 0. And now we take those derivatives. dV1 dx1 is 0. dV1 dx2 is sigma dot of time. It's a partial derivative. So the fact that this is a function out front is irrelevant. It's the partial derivative. And dV1 dx3 is 0. There are no x3s in there. What is sigma dot? It's this. So it's a little bit ugly, but it's manageable. We can just call it sigma dot and put this in later when we need it. So why were we doing del V? We were doing del V because we wanted del V plus del V transpose to get the tau. So we continue our march forward. That's del V. We can do del V transpose in our heads. So that means that gamma dot, del V plus del V transpose must be 0, sigma dot, 0, sigma dot, 0, 0, 0. And the stress tensor must be tau equals 0 minus mu sigma dot, 0 minus mu sigma dot, zeros. So for starters, psi 1 is psi 1 plus 0. Look back at the definition. It's tau 1, 1 minus tau 2, 2, and those are both 0. And psi 2 plus is tau 2, 2 minus tau 3, 3, which are both 0. So once again, the normal stress portions are 0. So nothing changed by making it unsteady flow. The normal stresses didn't change. But what about eta plus? The definition is minus tau 2, 1 over gamma dot naught. So it's minus mu sigma dot of t over gamma dot naught, mu sigma dot of t over gamma dot naught. Well, sigma dot of t is a function we know. Okay? It was given. It's sigma dot of t is equal to 0 for t less than 0, and it's equal to gamma dot naught for t greater than or equal to 0. So that means that for t less than 0, eta plus is 0. 0 goes in there and becomes 0. For t greater than or equal to 0, eta plus is equal to mu. We can sketch this. It's a function of time. Eta plus as a function of time is 0. And then it's gamma dot naught. If you put a Newtonian fluid into, say, a parallel plate device and don't move the top plate, but then suddenly at time t equals 0, you start moving the top plate at a steady rate, the viscosity should jump instantaneously. The measured viscosity function, eta plus, should jump instantaneously to the steady state value for all times. It's an interesting idea. Does it happen? It does happen for Newtonian fluids. It does not happen for polymers. It does happen to within our ability to start up instantaneously. The fluid is able to start up into. Let's take a look at some polymers. Yes. Oh, you're right. Thank you. I'm getting too casual. Exactly. It drops up to mu. Thank you. All right, so here's the summary, which is correct. This is now written in functional form. This is the stress growth function for steady shearing of a Newtonian fluid. And it jumps up to a constant value instantly at time t equals 0. And it predicts no normal stress coefficients. Do these predictions match observations? The answer is no, not for polymers. Yes for non-polymers, no, not for polymers. And these are data from the literature from Menzies and Gressley on the polybutadiene solutions, like the ones, in fact, the same ones we saw the steady shear viscosity results. And these are eta plus, the stress growth coefficient, as a function of time. And this is psi1 as a function of time. These are taken in a cone and plate apparatus. You can't measure psi2 in a cone and plate apparatus, so we don't know what psi2 is. Clearly, these are not zero. We're measuring quantities of 10 to the fourth dynes per square centimeter, dynes centimeter squared per square centimeter. It has funny units because of that gamma dot naught in the denominator. Okay? Clearly not zero. And here, clearly not instantaneous. Now, these are on a log scale. So if you did it on a linear scale, it would look a little bit more instantaneous. But clearly, here's 1 second. Okay? Clearly, a half a second into it, you can tell that it didn't rise instantaneously. And in fact, there was an overshoot. This is called a shear stress overshoot. This can be quite pronounced. Some materials have enormous peaks in shear stress overshoot. And that's flow memory happening. We're going to see that when we get to better constitutive equations. So the overall answer is, when we look at the details of what the Newtonian constitutive equation predicts, it fails on the normal stresses and it fails on the time effects. We can do other non-steady flows besides this startup one. And we've got a bunch. And I can assign you these as homework. I can say, take Newtonian fluid and predict it for all of these flows. Because for every flow, I'm going to give you the kinematics. I'm going to give you the material functions, and you can predict them. So this is steady. This is cessation of steady shearing. Here again is our velocity field. Here it's shearing for all times, and then suddenly we stop. We define the stress decay function as the shear stress divided by the shear rate that you were originally at. And the first normal stress decay and the second normal stress decay. Very, very similar looking definitions. What do they look like in real life? If you're shearing and shearing and shearing and then you suddenly stop, does it just stop? And the answer is, for a Newtonian fluid, it does, by definition, frankly, right? Because the Newtonian fluid is one that follows the equations we just predicted. But there are, in fact, fluids. Water will stop. But we saw even in the video, we saw he was kind of doing a stress cessation experiment this time. Do you remember that he twirled that around and then let go? Okay? He let go and it snapped back. Now, our experiment says, don't let go, but stop turning it. Okay? If we said let go, these would look differently. They would go back also. We didn't say to go back. We said shear and stop. Make the shear rate go to 0. Don't let it be anything else. And therefore, there was a little bit of stress pulling back on it, telling it go backwards. That's what these guys did. He sheared it a little bit and it went back. And that's what the measurements say. The stress decay function as a function of time depends on the previous shear rate, and there is a first normal stress effect. What does our little fake model predict? Well, it's going to predict no first normal stress effects. So this one is we made a little bit of progress with this one by fixing it up, by putting this fake function out front. And we were able to predict the steady shear viscosity response well, and this function is improved, which we'll talk about a little bit later when we talk about the power law model. But we did not succeed in fixing the normal stresses. There is no time dependence and no nonlinearities. So there's our takeaway lesson for today. To proceed to better constitutive equations, we need to know more about material behavior. We need to know more about time dependence. So we're going to discuss next more and different ways of shearing a polymer. It's still always shear flow, but how do we move that top plate? We've gone from 0 to something, something to 0. We're going to go to small amplitude oscillatory shear. And we're also going to go to the example that he used in the video of a constant stress on the top plate. That's going to be the most complicated one. And we're going to use all of this behavior as a way of deciding how should we fix up the constitutive equation to get one that's more accurate for the material observations that we see. Okay, so we'll continue that on Friday, and we'll also get the exam back on Friday.
Dr. Morrison, we still have homework 3 due on Friday?
Homework 3 was postponed till Tuesday.
Oh.